typically at the high energy ranges. So, So looking for dark matter at high energies, typically in the form of signatures in the forms of gamma rays or X-rays or cosmic rays. I'm going to take a very different approach in this talk and tell you about new searches that we're doing for dark matter at low energies. And in particular, it's a series of searches that a number of us have been developing in the last, say, 3 to 4 years that are sort of focused on using radio telescopes to try and look for signatures of axions in the magnetospheres of neutron stars. So since we haven't really heard an intro to axions, I just want to give you a very brief introduction. I know we have people working in solar physics and other fields that maybe don't deal with axions on a regular basis. So this is my 1 or 2 quick slide overview of axions. Generally speaking, there are 2 different types of axions that people discuss in the literature. There is the QCD axion, and there are axion-like particles. The QCD axion was originally introduced in the 1970s in order to address what's known as the strong CP problem. This is the question of why QCD seems to conserve charge parity symmetry. And that requires essentially a fine-tuning in the standard model of about 1 part in 10 billion. Axion-like particles are pseudo-Goldstone bosons, just like the QCD axion, but they were not introduced to solve the strong CP problem. They're a more generic, say, pseudo-Goldstone boson that appears. These are particles, however, that are extremely well motivated. String theories, for example, anything that predicts the compactification of extra dimensions generically gives rise to, for example, 50 or hundreds of these light, low-energy pseudo-Goldstone bosons. Now, at low energies, these new particles are coming along with 2 new free parameters, essentially the axion mass and what we call Fa, which is the axion decay constant. And that essentially sets the energy scale of that global symmetry that's broken that gives rise to the axion. Now, in the context of the QCD axion, these 2 parameters are actually related. And so you actually are left with a 1-parameter model described by either MA or FA. And in reality, there's a little bit of UV dependence. This is more like a family of 1-parameter models, but it's relatively simple. Axion-like particles don't have any correlation between the mass and the decay constant, so they have additional degrees of freedom. Now, the reason that we care about them today is usually that they constitute excellent candidates for dark matter. These things that can be produced very easily in the early universe, non-thermally and abundantly, and they behave essentially like pressureless fluids on large scales. So for all intents and purposes, these things look great, they're well motivated, and they look exactly like, for example, WIMP dark matter. Now, for the purpose of this talk, I'm going to be focusing on the electromagnetic interactions of axions, and in particular axions coupled to this combination of FF dual, that's the electromagnetic field strength tensor. And this is true generically for the QCD axion and axion-like particles, so I don't really need to make the distinction right now as to what I'm actually searching for. Now, this coupling to FF dual is really just a coupling to the electric field dotted into the magnetic field. And this gives rise to a really wide range of phenomenology. So for example, it allows for the axion to decay to 2 photons, 2 monochromatic photons. Oh, sorry, 2 monochromatic photons. This is a process that could be, for example, stimulated in the presence of background radiation, like synchrotron radiation in the galaxy. It allows for axions to mix with photons in the presence of external magnetic fields, and it allows for axions to be produced from non-orthogonal electromagnetic fields. Now, one of the strongest ways to look for axions is via this mixing of the axion and the photon in the presence of external magnetic fields. This is what Gabby talked about on Wednesday, and it's what most of the terrestrial-based laboratory experiments try to use to look for axions. Now, we can ask ourselves, how efficient is this process? Looking at the Lagrangian, you can sort of guess, essentially. You expect it to scale with the axion-photon coupling squared, the magnetic field strength squared, and by dimensional analysis, you can infer that what you're missing is essentially a length scale squared. Now, if you want a large conversion probability or large observational signatures to arise from this process, you need large magnetic fields and you need large length scales. Now, for mildly relativistic to non-relativistic axions, that length scale is essentially set by the inverse of the momentum mismatch of the axion and the photon. So in vacuum, you naturally expect this momentum mismatch to be extremely large. You have non-relativistic axions and you have relativistic photons. So that means that length scale is going to be inherently suppressed and this conversion probability is going to be extremely inefficient. Now, one way to get around this is to try and modify the photon dispersion relation. So you can do this by, for example, going to a cold isotropic plasma. In this case, you expect the photon momentum to pick up this extra factor omega p. That's the plasma frequency, which is set by the charged particle number density. And in this case, you see that if you were to find, for example, the optimal environment where the plasma frequency matches the axion mass, you would find that your momentum mismatch goes to 0. You resonantly enhance that length scale, and you can dramatically enhance your conversion probability. So we talk about where we want to look for this process. Our ideal environments are those where you have large magnetic fields and you have, say, for example, dilute plasmas. When you talk about large magnetic fields, there's no better place to go than the magnetospheres of neutron stars, where you have surface magnetic field strengths reaching 10 to the 15 Gauss. This is my diagrammatic illustration of the neutron star. We have something like a rotation of the neutron star about the z-axis. We have some slight misalignment between the magnetic axis and the z-axis, and we have some large poloidal magnetic field extending away from the neutron star surface. Now, I said we have large magnetic field, but what about the plasma? Well, if we allow this neutron star to rotate in vacuum, what you'll find is you'll induce an extremely large electric field. And that electric field is going to have a component that's parallel or perpendicular to the surface up here, and it's going to be strong enough to rip charges directly off the surface of the neutron star. Those charges will be accelerated to super high energies. They'll emit curvature radiation. That curvature radiation will pair produce. That'll emit synchrotron radiation, and you'll generate charged particle cascades. What that means is that even if you didn't start with a plasma, you're guaranteed to generate a plasma for free. Now, the charges are also going to respond to the presence of that electric field and rearrange themselves in the magnetosphere. And in particular, they're going to try to do that in order to cancel the induced electric field that was responsible for generating the charged particle production process in the first place. That is, you can try to look for a force-free static solution from this iterative charged particle production. And the solution that does that, or the charge distribution that does that, is typically known as the Goldreich-Julian model. This is a minimal condition on the charge density distribution. And we can ask ourselves, given this type of plasma, do we expect to produce these resonances in the axion-photon interactions, and if so, where? And the answer is yes, you do. And in fact, you can actually induce a resonance for any axion mass below about 10 to the minus 4 eV. All right, so let me contextualize what I've just told you so far. I said we want to use radio telescopes to look for axion-photon interactions in the magnetospheres of neutron stars. This is the axion parameter space today, where you see the axion-photon coupling sitting up here on the y-axis and the axion mass sitting down here on the x-axis. We have cosmological constraints on the axion in blue, astrophysical constraints on the axion in green, and terrestrial laboratory-based constraints on the axion in red. You can also see this bright orange band that's passing through the center of this plot. This is sort of the approximate parameter space that we associate to the QCD axion. Now, I've told you two pieces of information. First, I said we can ignite resonances for masses below about 10 to the minus 4 eV. That was actually based on a minimal charge condition. And in fact, we can actually probably do a bit better than that, so that we can probably induce resonances below, say, a few times 10 to the minus 3 eV. I also said we want to use radio telescopes. So we're talking about non-relativistic axions. We need to make sure that those axions have a mass or an energy above about 10 megahertz. Otherwise, you're going to find that those photons are efficiently absorbed in the IGM or in the Earth's atmosphere. And this sets a lower limit, more or less, on the characteristic mass range that we're looking at. So our window that we're going to try to probe is more or less sitting between 10 to the minus 7 and 10 to the minus 3 or so eV. Now, this is interesting for two reasons. First of all, you'll notice that other indirect searches, these conventional X-ray and gamma ray searches that Gabby talked about on Wednesday, are unable to really push into this mass range. The second reason is that this is actually the most well-motivated mass range to look for axions. This is the only mass range for which the QCD axion is expected to account for the entirety of dark matter. And what I'm going to try to convince you of in the rest of my 20-minute or 15-minute talk here is that we hope in the next 5 to 10 years to develop a search program in which we can push into that QCD axion mass range. All right, so there's sort of two things I want to talk about, two distinct processes which we can try to look for. The first one is the resonant production of radio photons from axion dark matter, and the second one is an idea that we've been developing about how we can actually source axions directly from the plasma dynamics near the neutron star itself. So let me start with part one. The general idea is if axions contribute to dark matter, you expect these axions to fall smoothly into the magnetospheres of neutron stars. Periodically, they'll encounter these resonances. They'll generate some photons. Those photons will undergo some nonlinear propagation, and then you can try to look for these things with our telescopes. And because axions in the galaxy are extremely narrow, extremely non-relativistic in energy, you expect that the characteristic photon dispersion energy dispersion is extremely narrow. Meaning what we're looking for is an extremely narrow spectral line that's approximately centered about the axion mass. Now, let me give you an idea of how we actually do these searches. I'm going to describe a search that we just finished at the end of or beginning of this year using the Green Bank telescope. This is a 100-meter single-dish telescope located in the US. We were gifted some data from the Breakthrough Listen initiative in the 4 to 8 gigahertz band. That's the C-band. At these frequencies and with these telescopes, you're talking about observing, say, the few inner parsecs of the galaxy. And we use an on-off target strategy, which was just described to us in the context of neutrinos, where you look for spectral lines that appear when you're on target that don't appear when you're off target. Now, when you're talking about looking at the inner few parsecs of the galaxy, you don't just have a single neutron star. You have hundreds, thousands, even hundreds of thousands of neutron stars that can convert. So we don't expect to see a single spectral line, but we expect to see some sort of forest of spectral lines that's Doppler broadened by the relative neutron star velocities and broadened by the individual plasmas around the neutron stars themselves. So this type of search really requires three distinct processes. You need to understand what that neutron star population looks like in the galactic center. You need to understand how to characterize your radio signal from each neutron star in your population. And then, of course, there's a huge amount of effort that goes into the data analysis, which I don't think I have time to discuss. But let's start here with population synthesis. All right, so we want to look and understand what the characteristic population of neutron stars looks like in the galactic center. The problem is we don't really observe any neutron stars in the galactic center. It's not because they aren't there, it's just because we have a strong observational bias on our population. This is what approximately what the neutron star pulsar distribution looks like that we do observe. You can see the galactic center, the center of this two-dimensional projected map. Earth is sitting out here at about 8 kiloparsecs to the left. And of course, you can see we're preferentially biased towards neutron stars that are closer to us. Now, what we can do is try to focus, for example, on the young neutron star population. Just focus on neutron stars that were born in the last mega year, for example. We do observe stars and star formation activity, for example, in the galactic center. So we can try to use the information on the stellar mass distributions and the star formation rates to estimate, for example, what the neutron star formation rate is. And because these things are so young, we can assume that the stellar distribution acts as a tracer for the neutron star distribution. And what that means is that we have rough estimates, for example, of what the characteristic number density of neutron stars are in these inner parsecs, as well as what the characteristic probability distribution of the neutron star birth rate is over the last, say, few mega years. We can also try to construct the conditional probability that tells us, given an age of a neutron star, what is the characteristic properties that define the magnetosphere, what is that period, the magnetic field, and the misalignment angle that describe the characteristic structure of charge densities in the plasma. And we can do that by essentially simulating populations and simulating magnetorotational spin down, and then fitting those to the observed pulsar distributions. So the only major assumption that enters here is that the characteristic pulsar distribution that we're observing out here is, roughly speaking, representative of the pulsar distribution that we expect to see in the inner parts of the galaxy. Okay, now for each neutron star in our sample, we need to determine what that actual radio signal looks like. The first step that we need to do is define the plasma structure of the magnetosphere. That structure of the plasma is going to define when we have these resonances and how efficient those resonances are. In particular, we expect those resonances to occur when the plasma frequency matches the axion mass, and we expect the efficiency of those resonances to be set by the gradients in the plasma along the surface. So this is a brief example of what that might look like for a typical pulsar. You expect to see something like a torus-like feature that wraps around the center part of that pulsar, and dome-like configurations extending around the magnetic poles of the pulsar. Now, this is for a fixed axion mass. If I were to lower that axion mass, you would expect that you need a lower plasma density or a lower charge density. So you expect the characteristic scale of that surface to increase away from the neutron star. And if I were to increase my overall axion mass, I need larger charge densities, so I push that closer to the surface of the neutron star. And eventually I push so far that actually the conversion surface disappears, and many of these neutron stars would no longer allow for resonant conversion. Okay, so then how do we actually go from the axion phase space at asymptotic infinity in the galaxy to what the overall radio signal looks like that we're going to be looking for with our radio telescopes? Well, we use techniques from geometric ray tracing. Essentially what we do is we define our conversion surface, which you've seen here just as before. We follow the axions as they fall onto the neutron star. We identify where those axions intersect the conversion surface. We understand how efficiently those things source photons, and then we ray trace the photons as they propagate out of the magnetosphere. Now, these photons undergo extremely nonlinear trajectories. It's a bit hard to see from this plot, but if you take a two-dimensional projection of one of those trajectories, you can see that these photons are heavily pushed around by the plasma and undergo extremely nonlinear responses to the plasma gradients. I don't have time to get into the details of why this is crucially important, but without this type of process, you would probably misestimate the radial flux by 4 or 5 orders of magnitude. Okay, so we do this for all the neutron stars in our sample. We repeat this ray tracing procedure for 10 million photons for each neutron star. We can then end up generating stacked profiles that are Doppler shifted by the relative neutron star velocities. This is what that looks like for 3 different axion masses of 17, 25, and 34 micro eV. A few things to point out. You can see the presence of individual neutron stars in our sample here. This is a particularly bright and a particularly narrow neutron star that appears across all 3 masses. You can also differentiate the effects of Doppler broadening from plasma broadening. Plasma broadening is setting the entire width of our forest of lines, whereas the plasma broadening is just broadening each individual line. And finally, you'll notice that as you go to higher and higher masses, you see that neutron stars disappear, and that's because you have less and less converting neutron stars in your population. All right, so these are the results for our search that we performed earlier this year. We did not detect any axions, not surprisingly, but we were able to set some upper limits on the axion-photon coupling across this 4 to 8 gigahertz band. These are the results for our maximally conservative fiducial model. Depending on the assumptions you make about the neutron star population modeling or the theoretical uncertainties in the mixing process or the plasma distribution, you can generate significantly stronger constraints. I would just want to highlight one thing here. We are quite far away from the QCD axion benchmark models that I've shown down here. We are exceeding current limits set by CAST, but I think one of the major optimistic things to look for in the future is the fact that there's a huge amount of uncertainties that we have yet to deal with. In particularly, there's a number of assumptions we made on the theory side, which are suppressing our signal unnecessarily by about 2 orders of magnitude. And there's a good reason to believe that SKA will be able to revolutionize our search for these things, as the collecting area is 2 to 3 orders of magnitude larger than the collecting area of GBT. So if I remove those uncertainties on the theory side, adopt slightly more optimistic assumptions, I also move from GBT to SKA, all of a sudden I expect my 10 sigma detection threshold to be very, very close to the KSVZ line. So very, very close to those characteristic QCD axion benchmark models. On top of that, we are able to push to lower and higher frequencies, meaning that there's a very good reason to believe that we could push this into the KSVZ line at higher masses. Finally, I just want to highlight the fact that we're not even exploiting time or frequency domain information, which in principle could give us an extra factor of few in the coupling. Okay, so that was part 1. I just want to highlight part 2, which is how we can actually source axions from the local plasma dynamics in the magnetosphere itself. The general idea is that in very localized regions of the magnetosphere, you expect the plasma to be unable to efficiently shield the electric field. In other words, you expect this E dot B term to be non-zero. These are the localized regions that are responsible for charged particle production mechanisms in the magnetosphere. Now, if you have a non-zero E dot B, what you'll find is that acts as a source term for axions. So space-time fluctuations will generate massive fluxes of axions that can escape the magnetosphere itself. As they escape, they can also undergo resonant conversion and generate a broadband radio flux. If those axions are non-relativistic, instead, they'll contribute to a growing axion cloud that can reach extremely high number densities around the neutron star. So let's take a look at what these the gap collapse process looks like in the magnetosphere. This is a zoom in on the polar cap of the neutron star, where the characteristic scales are, say, on the order of tens to hundreds of meters. The plasma has been unstabilized and flowed outward along the magnetic field lines. In doing so, you've opened up what we call a vacuum gap, where you have a non-zero or non-screened E dot B field. That electric field is once again sufficiently powerful enough to pull charges off the surface. Those charges will be accelerated in the electric fields, will emit the curvature and synchrotron radiation, will undergo these pair cascades. And as you do so, you're going to recollapse the gap. You're going to resuppress that electric field component. Now, the reason we care about this is, again, just because the Fourier transform of that E dot B variation is going to set our intrinsic axion spectrum. It's going to tell us how efficiently you can produce axions and what the intrinsic energy distribution of these axions are. This is a simulation that was generated by some of my collaborators, Fabio Cruz and Alex Chen. What I'm showing here is the space-time evolution of the electron charge density, the positron charge density, the gamma rays that are produced in this process, and the efficiency with which these things screen the electric field. I have to replay it every time. So I'm gonna play this a few times so you can see what's happening here. What you see are iterative charge particle bursts, charge particle cascades that are produced in this iterative process, both in the electron and the positron number densities. And as you see those bursts appear in these two plots, you'll see iterative screening or iterative damped oscillations in the paraelectric field. Sorry, I'm gonna play one more time. So you see the damped oscillations appearing here. These are occurring on characteristic scales of that Goldrake-Julian charge density. And we can use these simulations, because these simulations are actually made for somewhat realistic pulsars, to actually understand what the intrinsic axion spectrum looks like. And what you'll find is that you end up producing on the order of about 10 to the 50, 10 to the 54 axions per second in these very, very localized regions. That's a relatively large amount of energy density that you can use to generate radio fluxes. So we can essentially take those spectrum, we can propagate those axions out, we can look for where they encounter this resonant conversion surface, we can use that to end up generating broadband radio fluxes for these neutron stars, And we can go out and look for this, for example, for the nearby pulsar population. And if you do that, what you'll find is that for allowed values of the axion photon coupling, the radio flux that you find is, say, 6, 7, 8 orders of magnitude larger than what we observe. So we can actually end up constraining the axion photon coupling. We are in the process of actually turning this into a realistic bound at the moment. This has only been calculated for 3 fiducial points at 10 to the minus 8, 10 to the minus 7, and 5 times 10 to the minus 6 eV. But we are extending this to higher masses, where we expect to encounter the bound I just showed you in the previous slides, as well as lower masses where you expect to have a flatter spectrum. So this will extend to arbitrarily low axion masses. With that said, I think I'm almost out of time, so I want to conclude. I hope I convinced you that neutron stars are a powerful and rich laboratory in which we can try to probe axion physics. I know everyone here tends to be focused on the high energy regime, but there's a lot of interesting physics that's starting to be explored at low energies, in particular in the context of axions and axion dark matter, which offer fantastic candidates to try and look for. There's quite a few different observational signatures we can try to find, including looking for narrow spectral lines from resonant axion conversion. We can look for transient spectral lines that arise from the periodic encounters of neutron stars with over dense clumps of axion dark matter. And we can also look for broadband spectral features arising from the intrinsic axion production locally in the magnetosphere itself. So with that said, I think I'm in time for lunch.